We saw in the previous video that if I can rewrite a function as a polynomial function, it's very, very easy to apply the derivative rules that we learned today to take its derivative. So let's look at some functions that maybe aren't in polynomial form in terms of how they're presented to us, but maybe we can do some algebraic rewrites to get them into polynomial form. So the first thing that I want to look at is I want to consider the function f of x equal to 2x plus 1 times 3x minus 5. So a binomial times a binomial. And what I want to do is I want to find f prime of x. Now some of you may look at this and recognize that this is a product of two functions. It's the product of 2x plus 1 times 3x minus 5. And some of you also might be thinking back to limits, where limits worked very nicely with products. If I wanted to take the limit of a product, I could just take the limit of each individual factor and then multiply together the limit. And we said that the limit of a product was the product of the limits. Derivatives don't work out that way. In other words, what I can't do is I can't say the derivative of 2x plus 1 is 2 and multiply it times the derivative of 3x minus 5, which is 3, and say that f prime of x is 6. You cannot just simply do that with products. And so a special note here before we actually do take the derivative of this function, just to kind of reiterate what I just said, you cannot just take the derivative of each factor and multiply. The product rule for derivatives is not going to work as well as the product rule for limits. In fact, for products like this, we actually have a special rule. We will cover that rule, which is called the product rule. Not a terribly original name, but there it is. It's called the product rule, and that's going to be covered in topic 2.8. So in the very near future, we'll look at how to handle products of functions, but for right now, I can't just simply take the derivative of this piece and multiply it times the derivative of that piece. That is not going to be what the derivative equals. Fortunately, in algebra, we learned how to multiply this out and get it in terms of a polynomial. So I can expand out f of x, and I can do that by saying 2x times 3x is 6x squared. We know how to multiply binomials here. I'm going to get 2x times minus 5, which is negative 10x, and then this is going to be a 3x. So I end up with minus 7x and then minus 5. So that's what f of x is expanded out. You can see it's a quadratic function, and we kind of knew that from looking at this product as well. Well, if I take the derivative of this polynomial, the derivative of 6x squared, 2 times 6 is 12. Reduce the power, 12x to the 1 power, 12x. Derivative of 7x is just going to be 7, and it is minus 7. And the derivative of minus 5 is 0. So there's the derivative of f. It's 12x minus 7. And that's your answer right there. So for right now, and in fact in general, the easiest way is going to be to go ahead and multiply it out to get it to look like a polynomial. And so that's going to be the easiest way for you to take a derivative right now. We'll look at some other things later on where maybe I've got multiple terms or something like that that can be kind of nasty, and maybe some other rules would be more efficient. But for right now, go ahead and multiply it out to get it as a polynomial, because it's very easy to take the derivatives of polynomials. All right, let's look at one more type of function that we can do an algebraic rewrite on. Let's consider the function g of x equal to, and this is going to be a rational function, 3x squared plus x minus 1 all over x. And what I want to do is I want to find g prime of x. Same thing with products. Just like how I couldn't take the derivative of each factor and then multiply them together to get the derivative of the products, I'm going to have the same issue with quotients. I can't just take the derivative of the numerator and the derivative of the denominator and divide them off. I can't do what we kind of did with limits. Limits allowed us to do that with quotients. Derivatives will not. So very similar note here. you cannot just take the derivative of the numerator and denominator. That's not going to work that way. Instead, just like how we have the product rule that we'll cover later on in this unit, we also have something that we call the quotient rule. And we actually learn it in the subsequent topic, topic 2.9. So it's coming up very quickly on the horizon, but what I can't do is I can't say, hey, the numerator's derivative is 6x plus 1. The denominator's derivative would just be 1, so the derivative is 6x plus 1. It's not going to work out that way, as we'll see when we actually take its derivative. But because I have a single term in the denominator, and this only works when you have a single term in the denominator, I can actually rewrite g of x. I can expand it out. I can say that's 3x squared over x plus x over x minus 1 over x. And now if I do a little bit of simplification, I can actually rewrite g of x as a polynomial function. 3x squared over x is just going to be 3x. X over x is going to be positive 1. And then minus 1 over x is minus 1 over x. But if I'm thinking intuitively here, as we saw with the power rule, I'm going to go ahead and jump ahead. I want to write 1 over x as x to a power using a negative exponent. So this is going to be minus x to the minus 1. You'll pick up very intuitively as you become a master at taking derivatives that that's going to be a step that's going to benefit you nicely. So now I can take the derivative of each piece to find g prime of x. Well, the derivative of 3x is 3. The derivative of 1, remember, of a constant is 0. And then I can apply my power rule here to find the derivative of x to the minus 1. The minus 1 is going to come out in front, and so this actually becomes now plus x. And then I reduce the power by 1, so this is now plus x to the minus 2 power. And then I want to go ahead and simplify that without any negative exponents. So this ends up being 3 plus 1 over x squared. And that's actually what g prime of x comes down to. So if there's a single term in the denominator, it's usually pretty easy to split it up like this, simplify it down to a polynomial form, and then take its derivative. And again, if you need to rewrite it without negative exponents, you can. So that gives you a couple of ideas of how something maybe isn't in polynomial form, but you can rewrite it as a polynomial. And it actually makes taking the derivative a pretty easy process for those types of functions.